This is my reassessment for understanding of potential energy. Okay, so for this, I got the idea from the book, but I just changed it to where it's talking about Venus instead of Mars. Okay, so say we have a projectile, say like a satellite or a probe, and we want to launch it from the surface of Venus. You know, maybe we're Martians, and we need to know what launch speed we need so that it doesn't fall back down to the surface of Venus. Okay, so we have the universal gravitational constant. We know that that is, and wasn't really needed, but the gravity of Venus, I looked it up. We're able to use our formula, our velocity formula here, because when you think about the initial kinetic and gravitational energy, it's equal. It's going to be equal initially to finally, because we're assuming that the spacecraft reaches, the probe reaches we assume it reaches instantaneously its speed. So it doesn't matter, because as your gravitational potential energy is decreasing as it goes up, then the kinetic energy will be equally decreasing. No, equally increasing. Yes. Okay, so all we needed for our formula was the radius, which the radius of Venus, and the mass of Venus. So we put that in. Like I said, because the whole idea is that because the mechanical energy is constant, what you're gaining in kinetic energy, you're losing in you're losing in gravitational potential. No, maybe it's the other way around. The more I think about it, I'll just confuse myself more. So let me just go ahead and say what I think it is. Okay, so I put it in meters here. So we get the initial launch speed would have to be 10,360.4 meters per second, and in kilometers be 10.36 per second. Hope I explained it decently. I guess it's got to be the kinetic energy is increasing as the gravitational potential energy is decreasing, because it's getting further away every second. Yeah, I believe that's right. All right.